This is Taeyong from MIDAS IT. Please allow me to introduce myself. Here is contents of today's topic. When we perform analysis in FEM software, we probably make a structure using elements and input loads and define boundaries and then perform analysis. So I prepared today's materials to follow those steps. First of all, we will have a look at which structure is a target, which analysis method was used. And then we will check a model in detail and some functions for the numerical analysis. After this page, I will walk you through this as possible as I can. So the target structure is the Girder in the cable state bridge. So I'd like to talk about this cable state bridge simply. So this is cable state bridge. The total length of this bridge is 770 meter. It has superstructure, pylons, and piers. The superstructure could be the Girder, and pylon this, and pier is, you can see the both end side. The type of the superstructure is 3-cell pre-stressed concrete box Girder, and pylons and piers are planned as a concrete structure. This is today's topic. We will have a look at the transverse analysis of PSC Girder in the cable state bridge. This Girder is 3-cell box Girder, and it has tendon in the transverse direction. So these are the tendons in the transverse direction. We cannot get any results for the structure in the transverse direction from the analysis in the global system. Therefore, the main purpose of the transverse analysis is checking the capability of a Girder in the transverse direction. So we need to check member forces and components such as reinforcements, tendons, and the shape of the Girder. Let's move on to next slide. So in order to check several components, analysis results are checked under serviceability limit state and ultimate limit state load combinations. So these figures are example of SLS and ULS checking. So look at the right figure. I took the sections from the upper slab here and webs and bottom slab. As you can see, all sections were taken as the rectangle section in the transverse direction. And then all sections were checked under ULS combination. And this is a PSC zone. So there are tendons in the upper slab of the Girder. So I checked stress relievers at the top and the bottom side of the upper slab to verify the section under SLS combinations. So left figure show the comparing the result about stress and limitation of stress in the design code. I chose a modeling method before using software. These are two modeling methods for the transverse analysis generally. First method is 2D. It has beam elements. I know that this method is easy to model and check a Girder. And also it needs short analysis time. The second method is 3D. It has plate elements. And also it could be generated using solid elements as depending on the purpose. I know that this method allows to consider the global effects of each load cases. So I selected 3D model with plate elements for the transverse analysis. Here is the reason for that. First one, the vehicle load in 2D model should be replaced to distributed load on the upper slab. This is known for that it could be overestimated. Second one, the box girder shows complex behavior, and also the effect of cables should be checked. In addition, I needed checking the effect of several load cases more detail. Therefore, 3D model was used. So this is the sample model. Let's check the girder structure more detail to model the girder in software. This is a target model in the longitudinal view. As you can see, the girder consists of a normal section, cable anchorages, and leaves. And the several girder segments were considered to get more proper results from the analysis result. So the target is in the middle of the girder, but I modeled more the girder segment at the both end side. These are detailed sections of the girder structure. The girder types are three. First one, section A, is the normal section. It is 3-cell box girder. Second one, section B, is the normal section with leaves in each cells. As shown in the figure C, it can be considered that the upper slab has more thicker than the normal section. So these are the leaf. Last one, section C, is the normal section with cable anchorages and leaves in each cell. I guess that there is huge concentrated force in the middle of girder due to the cable force. So additional leaves in the inner box here were planned to reduce the effect. This is the messy detail of the girder. I planned checking critical sections at where section shape changes. And I took additional sections to get more results. So all of P's are sections where I got results from the analysis. After that, I drew element lines to create elements. I had two ways. Case number one is using the offset length. In this method, element lines are drawn in the opposite position from the standard line, such as the top of slab. So for example, this is a slab thickness. I draw the element line with the offset length here. And case number two is using the center of each part. In this method, element lines are drawn in the central location of divided section. So for example, here is a tapered section, and I can take their section for that, and I connected the center position of each section like this. Actually, two ways are available to use for element lines, but I wanted 3D plate element model. So if case number one is selected, the modeling work is simple. I just extrude the line element to the longitudinal direction. So in order to make modeling work easy, I selected case number one. So finally, I got the same element line for three types of Girder section. So as you can see, these are the same element lines. This is the plan view of the Girder. There are tendons, cable anchorages, and ribs in the Girder. They should be considered for modeling. Therefore, I planned their position are able to be divided. So this is divided position in the longitudinal direction. So red line are the plan. This plan was used for the offset length of elements when I extrude elements while modeling. So we have done to check the Girder structure and some plans for modeling. So let's move on to MIDAS civil. These figures are modeling steps. Exactly, these steps are regarding creating elements. In the first step, I prepared a drawing file for the Girder section as following the plan. So this is the drawing file. In the second step, I imported the drawing file into MIDAS civil. In the third step, I created plate elements for one segment of the Girder using extrude function. So I extrude this plane element to create a plate element. Lastly, I copied one segment several times to get a whole Girder shape. So I copied the one segment Girder and to get the whole Girder shape. After making the element model, I needed additional options to complete modeling work. First one is thickness property for plate elements. As you know, plate elements need the thickness property to have their stiffness. So I defined the thickness property. And then I assigned different thickness property into each element to consider tapered sections such as hunchy here and lips. Actually, plate element cannot have tapered thickness, so I used average thickness for the both end of one element. Next one is the dummy beam on the plate element. This element is for the tendon profile. I used tendon profile functions to consider pre-stressed loads. Tendon profiles in MIDAS civil provides us to consider the exact profile shape of a Girder, of a tendon. So it can control the eccentricity of tendon profile. This means stress releases can be controlled by tendon profiles. However, creating tendon profile is only available in the beam element. So I added the beam element on the plate element like this. These dummy elements share nodes with plate elements. The section of dummy elements was assumed as small rectangle section which doesn't affect total weight of the Girder. The last one is truss elements for cables. There are two options for cables in MIDAS civil. One is the truss element and the another is the cable element. I wanted to apply the cable force into the model of the linear analysis simply. So I used the truss element. Now modeling work is done. So next we will take a look which conditions will be used for load cases. I think it would be good to consider all conditions around the structure for better results. This figure is showing all load cases on the girder. There are self-weight of girders and barriers and pavement and pre-stress. And also we can see wind and different temperature, vehicle, and K force in the load case. Some loads can be replaced as the element model, and the others can be considered as static load cases, such as the nodal load, pressure, pre-stress, and so on. So on the next slide, we will check what functions in MIDAS Civil was used for all load cases. The girder body was considered using self-weight function, and barriers and pavement were replaced as plane load. The plane load function allows that it can be applied onto plate elements regardless of nodes and positions. Next one is wind load. As shown in the figure, the wind load was supposed to be on the side of barriers and the girder. So these are the wind load. The wind load on the barrier is replaced as the nodal load because barriers didn't be modeled. So I replaced this pressure as a nodal load case. And the wind load on the girder is considered as a pressure load. And uniform temperature was considered for heating and cooling cases. For that, element temperature function was applied. This is the pre-stress load. As shown in the figure, the tendon profile was considered. There are two types in the girder. So one is in the upper slab of the girder, and the another is in the leaves near the cable anchorages. The next one is vehicle. The vehicle load can be considered as the moving load cases of MIDAS Civil. The moving load analysis of MIDAS Civil is based on the influence line and surface analysis. It could be time-consuming work, so I used another method. This method is using all of wheels of a design truck. I put this load on the elements of the upper slab. So the wheel load is shown figure B. This is a wheel load. When I supposed the wheel load, I took account into Korean design code. The design code said the wheel load should be considered as the uniform distributed load in the contact area. So wheel load will be replaced as a discrete load like this. The contact area can be selected by an engineer as well. In this case, I considered the thickness of a slab to define the contact area because elements are placed inside of a slab. So the wheel loads are replaced as a uniform distributed load on the middle surface of the slab. So I took this UDL case. After selecting the vehicle load type, I figured out the location of the vehicle. In the longitudinal direction, I supposed cable anchorages as supports. So the girder structure can be considered like this continuous beam. And I changed the location of the unit load on the continuous beam to get the influence line diagram for the bending moment. So Through that process, I got this influence line diagram as shown in the figure. It is the maximum bending moment case at the middle of the girder. And then I put the vehicle load and adjust vehicle's position to get the maximum bending moment. So I moved this truck load left side and right side. So this truck is final position. This case is the position of the vehicles in the transverse direction. In this case, the top of webs is considered as the supports as overhanging continuous beam as shown this figure. Using this, I found influence diagrams for 3 cases. The influence line was found for 3 checking points. One is maximum member forces at the web here, and next one is at the cantilever. After that, I found the position of vehicles and the number of them through comparing various cases in the same manner of previous slides. So these are final position of vehicles under each case. And then I combined the location of vehicle in the longitudinal and the transverse direction. These figures are showing the location for each case. This is the model view which has the vehicle load as plane load in MIDAS civil. This is the cable force. I used pretension load function for cable forces. I got the data of cable forces from the global analysis model. And here, this is another approach for the cable force. This method is considering cable anchorages at point spring supports. The stiffness of point springs can be calculated using displacement ligatures against the unit load in the global analysis. So from global analysis, we can get the displacement ligatures for the cable anchorages. So, and then we can calculate the stiffness of spring, and then use the point spring function and with the calculated stiffness. Now we are going to look at the boundary conditions simply. I used define support function in MIDAS civil. In this case, the displacement of our direction was fixed at the end side of Girder here. Because I focused the analysis ligatures at the middle of Girder. Additional boundary condition options was applied into cable anchorages. First one is cable anchorage in the pylon. I suppose cable anchorages are fixed for all direction. And the anchorages at the girder were connected to the upper slab using the rigid link. After performing the analysis, I used load combination function to make load combinations under substability limit state and ultimate limit state. And then I use several options in ligatures function to check ligatures in the diagram of member forces and ligatures value in the tab format. This is an example of modification work. In order to check results under SLS combinations, I checked stress results of the upper slab like this. So the left one shows initial condition of the model and results. As you can see, the tensor stress is over the limitation at the middle of slab here. So that I added additional tendon profile into the lift at the cable anchorage here like this. And I got the reasonable results like this figure on the right. The results of the design is shown in the figure. In the final step, I adjusted reinforcement size, and to get reasonable design results, I removed some ribs which are not necessary. So these ribs are deleted. So today we took a look at the transverse analysis with MIDAS Civil. Maybe there are some different points of view in the analysis approach. I think this approach is one of various methods for the transverse analysis. In this case, I designed the Girder under the preliminary design step, so there are remained design items which are not considered in this design step. They could be punching shear of slab, shear resistance between the flange and web, checking displacement of cantilever zone for serviceability, and so on. These were considered in the detailed design step. In that case, our design team did additional design work to get more precise analysis result. They used another software called MIDAS FANX as well. This software supports various options for the detailed analysis. On a lighter note, this bridge is under construction in Korea at the moment.